Hi everybody, my name is Bryan Duggan. I am a computer science lecturer in the School of Computing in DIT. My talk this morning is about a project I'm currently working on with my colleague Owen Harris, who's also the CEO of Bitsmith Games, and he lectures in DIT as well. So we're working on this virtual reality game called Deep. So Deep is kind of a virtual reality experience. My colleague Owen has built a controller using an Arduino, and this controller actually responds to your breathing. And this experience that we're creating together is a sort of an underwater simulation. So essentially you breathe in and your character will float in underwater, and when you breathe out then your character sinks. It's sort of based around yoga breathing. And the idea is like that people will sort of train their breathing, and it's sort of going to be a relaxing experience. My particular role on the project is I'm kind of the AI programmer on it. So I've been teaching game engines since 2006. My sort of interest in computer games is more on the technology side rather than on the design side and on the visuals. So I'm very interested in physics simulation and AI. I have lots of projects up on my GitHub if anyone wants to take a look at them. So this talk that I'm going to give today, I'm going to give a really quick overview on how the AI is working for the fish, and I'm going to have loads of demos, so please bear with me if I switch between demos and PowerPoint slides and back to demos, and if things don't work, just please be patient, ask questions anytime, and I'll get started. Right, so first of all, what I'll do is I'll just show you a really quick video of some fish, and you can take a look at this. This is a real shoal of fish. And at the very end of the presentation, I'll show you the work in progress that I have on the fish in the Deep game, and you can tell, you can basically decide yourself if my simulation is approaching the sort of behavior that you see in this short video. So you can just see the fish do a number of things. They all kind of, I suppose, flock together. They move in at the same time. They all try and maintain the same direction. And then also occasionally the big fish will fly into the middle of the shoal of fish and will cause them all to disperse, and then they come back together again. So I spent a lot of time looking at fish and reading articles about fish and how they move and stuff before I started this project. Even though I've been working on these type of AI behaviors for years and years, I really love these kind of behaviors. They're incredibly, I suppose, what's the word? They're magical to program, you know. There's a really magical moment when you're programming steering behaviors for autonomous agents when the fish suddenly flock for the first time, and it's a fascinating and magical moment. So the framework that I'm using to program these AI fish, they're called steering behaviors for autonomous agents, and these are basically a framework for controlling autonomous agents. There's sort of three layers of AI. There's the sort of high-level decision making. In the middle, there's this sort of there's the steering behaviors, and at the bottom end, then you have what's called locomotion. And locomotion is basically the animations, you know, to make the things look like they move. But what steering behaviors for autonomous agents do is they sort of allow you to move things around the scene, to set up scenarios like tell your agent to start at one side of the scene, move to the other side of the scene, and if you happen to come in to contact with any obstacles along the way, we'll just avoid them. And the autonomous agent has got to figure out its own, obstacle avoidance and things like that. They're independent, so there's lots of different steering behaviors, but they can be combined together. So you can turn on stuff like separation, cohesion, and alignment behaviors, and that's what really causes the flocking. They can be also prioritized, so you can do things like an obstacle avoidance steering behavior has a higher priority than a seek steering behavior, so that so that you don't want your agents to crash into the scene. You could also, for example, prioritize a flee behavior. So if an enemy comes into the middle of the flock will just flee from the enemy and then will resume their flocking behavior. They're used in all kinds of different applications. My students for years have been programming space battles as their continuous assessment of this. So I provide them with the steering behaviors framework. They program some extra behaviors themselves, and they have to program space battles. So things like, we're looking at Battlestar Galactica and Star Wars and things like that for inspiration. And if you want to have a look, there's lots of videos of these simulations on my YouTube channel. So steering behaviors were invented by this guy. He's called Craig Reynolds, and his original steering behaviors paper was published at the SIGGRAPH conference. If you're familiar with that, it's a big graphics conference in 1987, and it's cited over 5,000 times. So just in terms of academic publishing, it's a really important paper. And he gave a keynote at the GDC, the Games Developers Conference, in 1999. I go to the Games Developers Conference most years, and there's always discussions and workshops about steering behaviors for autonomous agents. They're a really, really important concept in artificial intelligence for computer games. So I just have a couple of small videos. This first video is actually Craig Reynolds' original video from, I think it's 1987. And this is from his original kind of steering behaviors talks. He calls them boids in his paper, by the way. So I'll just show you, this is Craig Reynolds' original video from 1987 of his boids doing some flocking and avoiding some obstacles and things. So this, I guess, why, you know, this is, you can see that these are quite fish-like already. So this is why I chose this framework to implement my AI for my fish in deep. So there they are, avoiding obstacles and flocking around the scene. And this is like a sphere constrained behavior. So this is just a short video as well. This is one of the first movies that actually made use of these steering behaviors. And I think this was 1987 as well. This is a really weird movie. You can look it up on YouTube if you want to watch the whole lot. I won't show the whole lot. It's called Stanley and Stella Breaking the Ice. And as far as I can figure out, it's about a fish that falls in love with a bird. And they have some sort of relationship in it. But one of the sort of major, you know, notable features of this movie was the fact that all of these flocks were generated procedurally. There was no artist who positioned all the fish into their positions and got them to swim around. They actually procedurally swim around. So that's Stanley and Stella. So yeah, if you want, you can look at that on YouTube. It's only about 3 minutes long, but I think just in the interest of showing you some of the behaviors, I will I'll probably just cut that one off. Okay. So what is an autonomous agent? An autonomous agent maintains some state about itself, and it gets updated and drawn. You can enable and disable the behaviors, and it can also sense its environment and respond. So this is different to something like, you know, a rock or something which has just got state, but it can't respond to its environment. So this is an agent which knows its own speed and can perceive its environment as well. And this is the type of state, and this is exactly as you would imagine. An autonomous agent needs to know its position, it needs to know how fast it's going, it needs to know its mass. It has vectors which describe in which direction it's moving, what's its right vector, its up vector, and so on. And then some constraints like the maximum amount of force and the maximum amount of speed. And I'll just go through one of the behaviors. This is just a little bit of linear algebra which explains how the seek behavior works. So the agent is traveling at a particular velocity, and you want to get your agent to move to a particular point in the scene. So the first thing that happens is you calculate the desired velocity. And the desired velocity, you can see it as that grey arrow in the diagram above. And it's the velocity that you would like your agent to move in an ideal world. You would like it to instantly change from its current velocity to its desired velocity, which is to travel to its destination at its maximum speed. And if you return the desired velocity minus the current velocity, what you get is a force which, over a number of frames, will push the agent towards its destination. And that's the seek steering behavior. So now I will switch over, because I have loads of PowerPoint slides on steering behaviors, but I think much better if I actually show you these steering behaviors. This thing will switch over. It says no signal. Why is it saying no signal? I have a picture here. Why would it say no signal? Maybe it'll just come up by itself.
Can you move around?
Sure. Maybe if I just do Windows key.
Working.
Sure, so it says duplicate. You know what I'll do? What I'll do is I'll switch over to the demo, and I'll shut it down maybe and restart it.
Because when you first can you run the demo with a frame?
What's that?
Instead of full screen.
Yeah, I can do that. Actually, I'll demo window. Maybe that's better.
Yeah, demo window.
Yeah. Okay. Yeah. So all of these demos are written in Unity. All the code is on my GitHub. If anyone wants, you feel free to to clone my repository. Blank screen. Steering. This is the steering thing. I'll start the window maybe a little bit smaller. 800 by 600. That's enough so I can do the demos anyway. This normally works. Here we go. So I'm going to press function F10, which turns off rift mode. Function F7, function F7. That'll level the camera, change the camera mode. Function F7, which will level out the camera. Okay, so this is the first demo. I'll go through these steering behaviors really quickly. This is the seek steering behavior. This is what it looks like. So this agent, what I'm doing is giving it a position in the scene, and I think I can press function F2 to speed it up a little bit. There we go. So, yeah, there's a couple of things happening in this scene. So first of all, the little grey sort of dot, that's the seek position. And you can see that this agent, using that algorithm I just described, is actually seeking that point in the 3D scene. In this particular demo, and again, you can download all this code from my GitHub if you want, you can press function F1 and you can do a camera following behavior. So you can follow the boy around. So I will turn that off, function F1, function F1. There we go. The next behavior is called, that I have in this particular demo, is a pursue behavior. And in this behavior, there's one agent, the bigger agent is doing a random walk, so it's moving to a random position in the scene. The smaller guy is trying to anticipate its future position, so it uses a technique called dead reckoning, if you're familiar with that. So it's taking the speed of the speed that the smaller agent is traveling, the speed that the bigger agent is traveling, calculating how long it's going to take the smaller agent to get to the bigger agent, and using that to project forward a point in front of the bigger agent. And so the smaller agent is trying to intercept the bigger agent. So these are just some examples of the different behaviors that Craig Reynolds described in his original paper, and these are just implementations in Unity. This is a wander behavior. The wander behavior by itself, as described by Craig Reynolds, is kind of useless because the agent will just wander off the scene pretty quickly. So wander tends to work better, in my experience, if it's combined with lots of other behaviors. Next behavior I have here. This is a path following behavior. Path following behavior is kind of cool. You just set up a set of waypoints and your agent will move from one waypoint to the next. And so I'll start that one off again. It's 4 for the wander, and I'll just show you the camera following, and this is kind of cool. The other thing that I've implemented here, Craig Reynolds in his paper describes a technique called banking. So it's a way to kind of fake the rotation in 3D. And this works really well for spaceships, but obviously not for natural things like fish, because things in nature, things don't really bank, right? And also this is kind of fake rotations as well. What basically happens is the agent is traveling along and some acceleration gets added to the agent's up vector, which causes it to sort of turn, and then once the agent stops accelerating, the turning stops. So you can see that that's what that looks like. And you get this really realistic behavior. Again, this is kind of how things are done in movies, right? Even space movies which have zero gravity tend to implement this banking technique. But it looks, that's how we expect things to fly around, so it looks pretty cool. So function F1, oh, not function F1, it's 1 to turn off the camera following. Okay. Oh no, hang on, function F1 changes the camera mode. There we go. Next one, let's see, 5. Okay, this is actually just to show you how you can combine steering behaviors together. This is a really awesome steering behavior. It's called offset pursuit, and I'll actually turn on camera following for this because it's really cool. So what's happening in this particular scenario is the lead Boyd is implementing a seek behavior. So it is trying to get from one side of the scene to the other, but also it has an obstacle avoidance steering behavior turned on. And all of those little grey lines that you see are, kind of like feelers which get projected in front of each of the agents. And if they intersect with any of the obstacles, it'll calculate a lateral force, which will steer the object around the obstacle, and a braking force, and a lateral force which will steer it over and above the obstacles as well. All of those other agents are implementing an offset pursuit, so they will always try and stay in formation. And even when they go out of formation, they eventually will find their way back to their formation position. So this is like 3 or 4 different steering behaviors combined together, and you get this lovely. Oh, I'm pressing the wrong key here. I've set all this up myself. I should know what keys to press. So it's function F2 will change the speed. Yeah, there we go, and you can stop them all together. So they'll fly from one side of the scene to the other. So Craig Reynolds also described this behavior here, which is actually function F7, turn off the camera following function F1. There we go, and F7 to level up the camera. Okay. So this is really the behavior that I'm going for with my fish. And what this is actually a number of different behaviors, right? What I'll do is turn off the debug drawing so you can see debug drawing is F6. So you can see what it looks like. All right. So what's happening with these agents is every agent is implementing like probably about 5 behaviors, and they get combined together. The behaviors are number 1, separation. So if an agent finds itself too close to one of the other agents, it will generate a force to push itself apart a little bit. The second behavior is called cohesion. So if the agents find that they're too far away from their neighbours, they will generate a force to push them closer to the centre of mass of their neighbours. And the last behavior is called alignment. So the agents will look and see what direction their neighbours are travelling, and they will try and generate a force to push them in the same direction. So this one also has the wander behavior turned on as well. And interestingly, when you combine these three behaviors together, you get this emergent behavior. So the cool thing about programming these is you don't actually program the flock, you just program the individual behaviors. The flock just happens by itself. So there's a kind of a magical moment when you realise your flock is actually flocking. They're also avoiding those kind of spherical obstacles as well. So that's theory behaviors for autonomous agents. If you want the code, you can get it on my GitHub, right? Now the last thing I'm going to show today is I just want to show a quick demo of the deep work in progress. If anybody wants to have a look at this for real with the breathing controller, we will be demonstrating this with the breathing controller in VR Wednesday next in the Odessa Club from about 6:30 at an event called Dublin, which is a game developers meetup group where lots of game developers come and show their prototypes. So what I'm showing you today, I've disabled lots of stuff in this, so there's no VR, there's no breathing controller. Basically you'll just get a little bit of the scene. Hopefully this will work and you'll be able to see it. Nothing so far. Yeah, this looks like it's good. It's meant to come up black like this at the start. That's good. It does take a few seconds to start. I haven't quite figured that out yet. I got this working at 1 o'clock in the morning last night. So this is deep, okay? So first of all, I have a first-person camera controller attached to the player just right now, just so that I could demonstrate this, okay? And there's lots of beautiful procedural 3D environment, and there's some lovely audio which you get in this simulation as well. You can see all my fish over there. So these fish have another few behaviors. When you're in this simulation, you'll essentially start at that starting point. You're going to float down this little area down here. You breathe in and breathe out the whole time. Your character's going to move very slowly, and eventually you end up on this little area here, and you've got all these beautiful procedurally generated and procedurally drawn fish. So there's a few cool things happening here. First of all, they're all procedurally drawn. There's no 3D models, there's no sprites. Next of all, I have a procedural animation on the fish, and the procedural animation is timed to the acceleration. So the fish will basically, what do fish do? What's that thing called? Their tails wag, depending on how they're accelerating. So there's also a behavior which I haven't entirely got working right, where they're avoiding the scene, but they do tend to get stuck in certain areas. As you can see, some of them are stuck there. I know how to fix that, I just haven't got around to it yet. But they're flocking. They're entirely procedurally flocking, and hopefully you'll get this really nice experience. The other thing that they'll do is they'll flee from that red guy. The red guy is just doing a random walk around the scene, and they'll flee from him. They'll also flee from the player if you get too close to them. So this is just the flee behavior has a higher priority than all of the flocking behaviors. And I'll just let them flee like that. You can see they'll flee. When they do get stuck, like if occasionally they get stuck, you can just make them. There's also no collision detection on the camera in this little simulation. Like these guys have kind of got stuck here. So I can just come over here and they'll all flee away. We are going for this flat shaded 3D look, we're not trying to make this photorealistic simulation or anything like that. And there's lots of other things which I've disabled in this just so you can see the fish, like there's fog and stuff, but I've disabled it because you get a better look at how the fish work. So I'll just leave that running and I'll take any questions now.
First, thank you very much.
Thank you.
Any question? Yes.
It's okay. Okay. In the wandering behavior, you said there's a lead fish. Why does the lead fish get selected?
See, it depends. You program it in the flocking, or no, the offset. That was the offset pursue.
Yeah.
So I just set it up. I've given one fish in the previous simulation. I gave one of the voids a behavior to seek a point in the scene, and the other voids are offset pursuing that main void. But they all have the obstacle avoidance one turned on. So the first void will just seek and obstacle avoid. The remaining voids will do the offset pursue, which causes them to stay in formation, and they'll also avoid the obstacles as well.
And in a real world example, like in sort of, how does it just not random procedural?
Yeah, so a real world example would be maybe if you think of airplanes flying in formation. One guy takes the lead and the other guys all take sort of, they stay in formation. So that's a real world example. Does that answer your question?
Yeah.
Anybody else want to
Yeah.
ask me? Yeah.
Was the same techniques used in Pixar's Finding Nemo?
Good question. Probably. I mean, these are standard techniques used in movies. The very first movie to use it was the Batman Begins movie, which was all the way back in, I think, 1992. And it was used to simulate the penguins. You know, there was a big march of penguins through the city, and that used this technique. Stuff like the Lord of the Rings movies use these techniques as well. You know, where you have like battle scenes with thousands of NPCs. Well, they wouldn't be NPCs in the movie, but thousands of agents, you know, attacking whatever. They use these same techniques as well. So they're kind of standard techniques in games and movies in order to simulate crowds and flocks of things.
Which of the techniques is more mathematically CPU intensive?
They're all really simple. They're all very simple linear algebra things. The problem is the actual kind of flocking algorithm itself is an ON squared algorithm, if you know what that means. Because every time you add an extra one, it basically squares the number of neighborhood calculations that need to be made. There's an algorithm called cell space partitioning which can reduce it to ON, but still you need to use all kinds of space partitioning algorithms. Otherwise, I can kind of simulate between 200 and 300 voids and then things start slowing down. Otherwise, you can do things on the GPU as well. I mean, I've seen people do like 10,000 voids on the GPU, but I don't know how to do that in Unity, so yeah.
Yeah, sorry.
The agents are all aware of the other one, or they're just aware of the ones that are close to them?
They're just aware of their neighborhoods. So you can get different effects by changing the neighbor distance. Like they will be more flocky depending on how big you make the neighbor distance. Also, like a simple thing that I haven't done, you know, I'm just using a distance calculation to figure out who's a neighbor, but really what I should be using is distance plus field of view. Because if you think of a fish, you know, a fish might be aware of a fish behind it, but it's only aware of fishes in front of it.
Do you think that this could be implemented with drones, real drones?
Sorry, with what?
Real drones.
Oh, drones. Yeah, this is the same techniques as used for robotics as well. I mean, all of these steering techniques are used, you know, for robotics as well, yeah.
Okay, all right, that's a question.
So I seen that whenever the fish trying to avoid the object, it also try to collapse with the neighbor.
Yeah.
So like my question is that like instead of every fish trying, like they do have the nature of avoid the obstacles,
Yeah.
but like instead of having a focal point on the main object, why don't they just focus on the neighbors or the front of the one? So if the front try to avoid the object, the one behind automatically do the avoid.
Yeah, it gets very complicated. I mean, it's a problem I'll have to